Alright, let's go. Number 12, the energy that will not switch off. Max Planck in 1911 was not hunting for a new form of energy. He was trying to soften his own revolution. His first radiation law had forced energy into discrete packets, and he disliked how radical that looked, so he built a second version where only emission was quantized. It was a retreat, not an advance. The physics of the time was clear about the bottom of the temperature scale. Absolute zero means no thermal motion. Every oscillator comes to rest. That is what the word zero is doing in the phrase. Out of Planck's algebra came a term he had never inserted. At absolute zero, each oscillator held onto half a quantum of energy. The equations would not release it. The value is hf divided by 2. Albert Einstein and Otto Stern argued in Annalander Physik in 1913 that the term was physically real. Robert Mulliken settled it in Physical Review, Volume 25, page 259 in 1925, measuring the band spectrum of boron monoxide. The isotope shift between boron 10 and boron 11 only matched the data if the half quantum was there. Every escape route closed. It was called an arbitrary choice of energy zero until Mulliken proved it changed observable spectra. It was called unobservable since only differences matter, until helium refused to cooperate. Heike Kamerlingh-Onnes could not freeze helium at any temperature he could reach, and Willem Keesum solidified it in 1926 only under 25 atmospheres. Zero-point motion keeps helium liquid at absolute zero. It was called a term you may subtract by convention, until gravity was found to couple to absolute energy density. The room around you cannot be emptied. Pump out every molecule, cool the walls toward absolute zero, shield every field, and what remains is not nothing. It is a medium at its lowest setting, which is not off. What is the true energy of empty space, and why does the only theory that can calculate it give a number the universe visibly ignores? That abstraction became a measurable push within 4 decades. Number 11, the force from nowhere. Hendrik Casimir was at Phillips Research Laboratories in the 1940s, and his assignment was industrial. Phillips made colloidal suspensions, and they were misbehaving. Attraction between particles fell off faster than van der Waals' theory predicted. This was a materials problem for a lighting company. Electromagnetism has a firm rule about the space between 2 neutral metal plates. Nothing is there. No charge, no current, no field. 2 neutral objects held apart in a vacuum should feel no force between them. The gap is inert. Casimir and Dirk Polder worked out the retarded correction in Physical Review, Volume 73, page 360, in 1948. Then Niels Bohr told Casimir the result had something to do with zero-point energy. Casimir reformulated it entirely. His 1948 paper in the Proceedings of the Koninklijke Nederlandse Academie van Wetenschappen, Volume 51, page 793, gave a force per unit area of pi times h bar times c, divided by 240 times the separation to the 4th power. Plates restrict which vacuum wavelengths fit between them. Fewer modes inside than outside means more pressure outside. At 10 nanometers, that pressure reaches 1 atmosphere. Steve Lamoureux measured it in Physical Review Letters, Volume 78, page 5 in 1997, matching theory within about 5%. Umar Mohideen and Anushree Roy tightened that to about 1% the following year. Each alternative was tested and pushed aside. Residual patch potentials on the metal were mapped and subtracted. Surface roughness was measured with atomic force microscopy and corrected for. Ordinary van der Waals attraction describes the short-range limit, but fails on the geometry dependence further out. The one live dispute is not whether the force exists, but how to model the metal at finite temperature, and physicists have fought over the Drude plasma models for 2 decades. Engineers now design around this force in microelectromechanical devices, because at nanometer scales, the vacuum reaches across the gap and sticks their components together. If empty space can push hard enough to jam a machine, in what sense was the space ever empty? The same medium was hiding somewhere far smaller. Number 10, the shift inside the atom. Willis Lamb spent the Second World War at the Columbia Radiation Laboratory building microwave technology for radar. When it ended, he had magnetrons and waveguides no atomic physicist had ever possessed, and he wanted to point them at something. He chose hydrogen because it was the simplest available test target. Paul Dirac's 1928 equation made a celebrated prediction about hydrogen. 2 levels labeled 2s1/2 and 2p1/2 sit at exactly the same energy. They are degenerate, not approximately. This was an exact consequence of the most successful equation in atomic physics. Lamb and his student Robert Rutherford found the levels were not equal. One sat above the other. The the gap was small, stubborn, and unmistakable. The result appeared in Physical Review, Volume 72, page 241 in 1947. The measured splitting was about 1,000 megahertz. The modern value is 1,057.8 megahertz. Hans Bethe heard the number at the Shelter Island Conference in June 1947, worked the non-relativistic calculation on the train home, got 1,040 megahertz, and published in Physical Review, Volume 72, page 339, the same year. The failed explanations are instructive. Experimental error was assumed first, and Lamb's method was cleaner than optical spectroscopy by a wide margin. A missed relativistic correction was proposed next, and the Dirac equation is already fully relativistic. A modified Coulomb potential broke agreement everywhere else. Simeon Pasternak had seen hints in optical data in 1938 and been ignored. The real obstacle was that the honest field theory calculation gave infinity, and it stayed infinite until Julian Schwinger, Richard Feynman, Shinichiro Tominaga, and Freeman Dyson built renormalization. The electron in the hydrogen atoms inside your body is not orbiting quietly. It is jostled continuously by vacuum fluctuations, and that jostling smears its position enough to move the atom's energy. The framework describing all matter was rebuilt to accommodate one number found inside the simplest atom. Was that a repair or a confession? Precision then became the vacuum's most damning witness. Number 9, the number checked to 12 decimal places. Polycarp Cush and Henry Foley were running atomic beam magnetic resonance at Columbia in 1947, characterizing how gallium atoms respond to magnetic fields. Careful, unglamorous structural work aimed at atoms rather than at the foundations of physics. Dirac's theory again made a clean prediction. The electron's G factor, relating its spin to its magnetic moment, should be exactly 2. A pure integer falling out of the equations with no adjustable parameter anywhere. They found it was not 2. It was larger by roughly 1 part in 1,000, and the excess was real. Their result appeared in Physical Review, Volume 72, page 1256 in 1947. Schwinger calculated the leading correction as the fine structure constant over 2pi, 0,161. The modern value from Xing Fan, Thomas Myers, Benedict Sucre, and Gerald Gabriels at Northwestern in Physical Review Letters, Volume 130, page 701 in 2023, gives G over 2 as 1 plus 1 plus 5 plus 9 by Knox 5 2 859 to 13 parts in 100 trillion. It is the most precisely measured property of any elementary particle. Nearly all of the excess above 2 comes from the electron interacting with virtual particles. Remove the vacuum contribution, and theory misses experiment in the 4th decimal place. Explaining it by a finite electron size was killed by scattering experiments, constraining the electron below 10 to the minus 18 meters. Blaming unknown heavy particles collides with a standard model calculation, taken to 5 loops, that already matches. The open wound is that testing this needs an independent value of the fine structure constant, and the 2 best measurements from Berkeley using cesium in 2018 and the Kassler-Brossel laboratory in Paris using rubidium in 2020 disagree by more than 5 standard deviations. Every magnetic property of every atom in your body depends on this number, and its value is set by particles that never exist long enough to be detected. We have confirmed empty space to 12 decimal places while failing to agree on the constant we measure it in. The vacuum then stopped being a correction and became the source of mass. Number 8, the field that decides what things weigh. Philip Anderson was a condensed matter physicist working on superconductors. In 1962, he was asking why photons behave as though they have mass inside one, a practical question about penetration depth in metals. He published it in Physical Review, Volume 130, page 439, in 1963, a solid-state paper. The gauge theories describing particle forces had a fatal problem. Their symmetry demanded that force carriers be massless, like the photon, but the weak nuclear force is short-ranged, which requires heavy carriers. The symmetry and the world contradicted each other directly. The resolution, generalized from Anderson's metal, was that the symmetry is not broken by the equations. It is broken by the vacuum. Space sits at a non-zero value of a field, and particles moving through that value behave as though they have mass. Robert Brute and François Englert published in Physical Review, Letters Volume 13, page 321 in 1964. Peter Higgs published in the same journal, Volume 13, page 508 after Physics Letters rejected his first version. The vacuum expectation value is 246 giga-electron volts. The particle was found on the 4th of July 2012 by Atlas and CMS at CERN, both papers in Physics Letters B, volume 716 at a mass near 125.2 giga-electron volts. The problem it created is worse than the one it solved. A Higgs mass of 125 giga-electron volts should be dragged by quantum corrections toward the Planck scale, 10 to the 19th, unless enormous separate contributions cancel to roughly 30 decimal places. Supersymmetry was built to enforce that cancellation, and the Large Hadron Collider has found none of its particles. Technicolor was excluded by precision electroweak data. Large extra dimensions predicted signatures that never appeared. What remains is the proposal that our value is 1 of 10 to the 500 possibilities across a landscape of vacua, which no experiment can falsify. Your mass is not stored inside your particles. It is what your particles feel while moving through a setting that space happens to be holding. Why space holds that particular setting out of an unimaginable range of others has no accepted answer. Push that field hard enough, and the theory says it hands you matter. Number 7, the threshold where the vacuum breaks. Fritz Sauter in 1931 was cleaning up somebody else's confusion. Oscar Klein had raised a paradox about electrons meeting steep potential barriers and appearing to pass straight through. Sauter worked the barrier problem properly. Werner Heisenberg and Hans Euler extended it in Zeitschrift für Physik, volume 98, page 714, in 1936. A static electric field carries energy without carrying particles. A constant field in empty space should sit there indefinitely, pushing on whatever charge you place in it and producing nothing on its own. Fields do not manufacture matter. Above a certain strength, the equations say the vacuum stops being stable. Electron-positron pairs are torn out of it as real particles. The field, in effect, rips. Julian Schwinger derived the rate in Physical Review, volume 82, page 664, in 1951. The critical field is the electron mass squared times c cubed divided by E times h bar, 1.32 times 10 to the 18th volts per meter. In laser terms, in intensity near 4.6 times 10 to the 29th watts per square centimeter. Below it, production is exponentially suppressed, which is why nobody has seen it. Every route has stalled. Direct laser production falls short by 6 orders of magnitude. The record-focused intensity from the Center for Relativistic Laser Science in South Korea in 2021 is 1.1 times 10 to the 23rd watts per square centimeter. Boosting the effective field in an electron's rest frame helped. And the SLS E144 experiment in 1997 saw multiphoton pair production, a related but different process. Heavy ion collisions exceed the critical field for far too short a time. Graphene analogs published in Science in 2022 reproduce the mathematics in a solid, which is suggestive and is not the vacuum. The prediction sits inside the same theory that gave the electron's magnetic moment to 12 decimals. Not a fringe idea, simply out of reach. If empty space can be forced to produce matter, what exactly separates something from nothing? A weaker version of that effect has already been achieved in a laboratory. Number 6, the mirror that shook light out of nothing. Christopher Wilson's group at Chalmers University of Technology in Sweden built superconducting circuits for quantum information, tunable microwave resonators, squids, controllable devices. The vacuum was not the target. The apparatus turned out to be capable of something else. Gerald Moore had shown in the Journal of Mathematical Physics, volume 11, page 2679 in 1970, that a mirror moving at relativistic speed converts vacuum fluctuations into real photons. The catch was the requirement. A physical mirror would have to oscillate at a serious fraction of the speed of light. Matter cannot, so the prediction sat untested for 41 years. Wilson's group did not move a mirror. They modulated the electrical boundary condition at the end of a transmission line using a squid, shifting the effective mirror position without moving any mass. The result was published in Nature, volume 479, page 376 in 2011. The effective boundary moved at roughly 5% of the speed of light, driven near 11 gigahertz, and the circuit emitted microwave photons out of a vacuum state. Pasi Leitain-Maki and colleagues at Aalto University confirmed it with different hardware in the Proceedings of the National Academy of Sciences, volume 1 and 10, in 2013. The objections were specific and each was answered. Thermal photons from the refrigerator were the obvious candidate, and the emissions scaled with drive frequency rather than temperature. Amplifier noise was ruled out by the correlation structure. Photons arrived in pairs, symmetric around half the drive frequency, correlated in a way noise cannot imitate. Amplified pre-existing photons were excluded because the output was squeezed vacuum, with the statistics of pairs created from the ground state. The surviving criticism is semantic, that this is parametric downconversion in grander language, and it concedes the physics while disputing the poetry. Somebody built a machine, shook the boundary of empty space, and light came out. That has been done. It is in the literature. If the ground state of the universe emits light when disturbed, what else is it holding that we have not learned to shake loose? The next result questions whether emptiness is a property of space at all. Number 5, the vacuum that is warm if you run. William Unruh was trying to understand what Stephen Hawking had just done. Hawking's 1974 result said black holes radiate, and Unruh wanted to know where the radiation came from, whether it belonged to the horizon or the observer. Stephen Fulling had already found something strange in Physical Review D, Volume 7, page 2850 in 1973, and Paul Davies extended it in 1975. Quantum field theory defines a vacuum as the state containing no particles. That definition is supposed to be objective. Either particles are present or they are not, and every observer agrees, the same way everyone agrees a room is empty. Unruh showed the definition is not observer independent. An accelerating detector moving through the region an inertial observer calls empty clicks. It registers a thermal bath at a definite temperature. The result appeared in Physical Review D, Volume 14, page 870 in 1976. The temperature equals h bar times the acceleration divided by 2 pi times c times Boltzmann's constant. About 4 times 10 to the minus 21 Kelvin for every meter per second squared. Reaching 1 Kelvin needs an acceleration near 2.5 times 10 to the 20th meters per second squared. Nobody has detected it, and the attempts read as near misses. John Bell and John Linus proposed in Nuclear Physics B in 1983 that electrons circulating in a storage ring should show it as an anomaly in their spin polarization, and the depolarization observed at LEP was consistent with the effect and equally consistent with conventional Sokolov-Chernoff physics. Ultra-intense laser schemes need the field strengths entry 7 cannot reach. Bose-Einstein condensate analogs reproduce the mathematics in a fluid rather than in space-time. Some theorists called the effect a coordinate artifact, and the standard reply is that a physical detector physically clicks, which no coordinate choice can arrange. Sitting still, you call the space around you empty. Someone accelerating past you through the identical region would measure it as warm. If two observers at the same point disagree about whether particles exist there, which one is describing reality? Everything so far confirmed the vacuum is real. Now we try to weigh it. Number 4, the worst prediction in the history of physics. Yakov Zeldovich was reconciling two accepted theories in the late 1960s. Einstein had put a cosmological constant into general relativity in 1917 and later abandoned it. Zeldovich asked a plain accounting question. If field theory gives empty space an energy density, and relativity says energy gravitates, then vacuum energy must appear in Einstein's equations as exactly that constant. Both theories were extremely well tested. Field theory had produced the electron's magnetic moment to 12 decimals. General relativity had passed every solar system test. Combining two successful theories where they clearly overlap should give a sensible number. It gave a disagreement of 120 orders of magnitude. Steven Weinberg laid it out definitively in Reviews of Modern Physics, Volume 61, page 1 in 1989. Summing vacuum fluctuation energies up to the Planck scale gives a density near 10 to the 93rd grams per cubic centimeter. The observed dark energy density is near 10 to the minus 29th, an energy scale of 2.3 thousandths of an electron volt. The ratio is 10 to the 120th. Wolfgang Pauli had noticed the problem decades earlier and calculated that such a universe would have a radius smaller than the distance to the moon. Every fix has failed in a documented way. Supersymmetry would cancel bosonic against fermionic contributions exactly, but it is broken at accessible energies, leaving a residue too large by 10 to the 60th. Quintessence replaces the constant with a rolling field and never explains why the constant part is absent. Weinberg's own anthropic argument in Physical Review Letters in 1987 correctly predicted a small non-zero value before it was measured, at the price of a vast ensemble of unobservable universes. Unimodular gravity and sequestering remove the term by construction rather than explanation. The energy in the space your body occupies is either the largest quantity in physics or one of the smallest, depending which correct theory you ask. How does a field that measures one number to 12 decimals get another wrong by a factor of a googol? Observation then made the problem physical rather than theoretical. Number 3, the 68% that might be your living room. Saul Perlmutter's supernova cosmology project and the High Z supernova search team led by Brian Schmidt were racing to measure a deceleration. Everyone assumed gravity was slowing cosmic expansion. The only question was by how much, and therefore whether the universe would recollapse. Both used type Ia supernova as standard candles. A universe containing only matter has one option. Gravity attracts, so expansion must slow. The measured value could be large or small, but the